Most people believe the Earth has about 5 billion years left before the Sun expands and swallows it. But advanced models reveal our planet's biosphere will actually suffocate in just 500 to 600 million years. As the Sun gradually brightens, rising temperatures will accelerate silicate weathering, drawing critical carbon dioxide out of the atmosphere until plants literally starve to death. Once the plants die, atmospheric oxygen will rapidly crash to roughly 1% of present levels, the ozone layer will completely vanish, and all complex animal life will suffocate and burn under lethal ultraviolet radiation. We are much closer to the absolute limit of Earth's habitable lifespan than we ever imagined. So, how exactly do we survive a deadline we didn't even know we had?
Well, it sounds utterly terrifying, right? But I promise you, this isn't the end of our story. In fact, it's the ultimate beginning. We're going to explore the biogeochemical collapse that's coming for us, our initial Mars architecture, how we'll have to hack our own biology for the void, the creation of unimaginable megastructures, our interstellar escape plan, and finally, how we'll find a brand new Earth. You see, humanity possesses something no other species in the history of our planet has ever had: the cognitive capacity to anticipate the death of our world and literally engineer a way out. We're currently standing at this wild intersection where theoretical physics, aerospace engineering, and synthetic biology are all coming together, and they are drawing up the greatest escape plan ever conceived.
But to fully appreciate where we're going, according to me, we need to first understand that invisible ticking clock right beneath our feet. We need to look straight at the 500 million year deadline. Now, what's truly terrifying about our biological clock is the sheer unavoidability of the timeline. And it all starts with the Sun. Since it formed 4.5 billion years ago, our star has been steadily, relentlessly getting brighter. As it fuses hydrogen into helium, that leftover helium ash is super dense. It sinks down to the core, ramps up the internal pressure, and basically forces the star to burn just a little bit hotter. We're talking about a seemingly marginal 10% increase in brightness every billion years. Doesn't sound like much, right? But for Earth, that 10% is an absolute death sentence. Just looking at the milestones here, in a mere 500 million years, plants face a mass extinction from carbon dioxide starvation. By 1.08 billion years, our oxygen completely crashes. And by 1.5 billion years, the ambient heat gets so unbearably intense that our oceans literally begin to boil away into the atmosphere. It's an unstoppable, cascading failure of the entire biosphere. Okay, so you might be wondering, how does this happen so fast? We have to talk about something called the carbonate-silicate cycle. Think of this as the Earth's giant planetary thermostat. Right now, it keeps our global climate perfectly balanced. But as the sun gets hotter, evaporation goes way up, and this accelerates the weathering of surface rocks. When these silicate rocks weather, they go through a chemical reaction that literally sucks carbon dioxide straight out of the air. It washes it down into the oceans, and it gets permanently trapped in limestone on the seafloor. Because the rising heat constantly accelerates this process, the Earth is essentially forced to absorb almost all of its own atmospheric CO2 into solid rock. This is the crucial bottleneck. Plants rely entirely on that atmospheric CO2 to breathe and photosynthesize. As those levels plummet, 99% of plant life, we're talking every forest, every jungle, every single blade of grass, will literally starve to death. So what happens when the lungs of the Earth stop breathing? The foundation of the entire global food web just completely collapses. Whether we're looking at terrestrial insects or marine life, the data clearly shows the massive decline begins right around that 500 million year mark. And look, the final blow for animal life won't be a slow, quiet fade into the dark. It's going to be exceptionally brutal. As the ozone layer vanishes without oxygen, lethal UV radiation will just scorch the barren surface. On top of that, recurrent geological heat waves will routinely push global average temperatures past 46 degrees Celsius. That's about 115 degrees Fahrenheit. That right there is the absolute biological survival limit for almost all complex animals. The proteins in our bodies simply break down. We overheat, and we die.
Ultimately, I want you to imagine our beautiful, thriving, vibrant blue biosphere completely transforming into an alien wasteland. Because as the oceans boil from that runaway greenhouse effect, massive amounts of water vapor rise into the upper atmosphere. Up there, solar radiation will blast those water molecules apart. The lighter hydrogen will literally bleed away into deep space forever, permanently dehydrating the planet. Fast forward 1.5 to 2 billion years, and Earth won't even be Earth anymore. It's going to look exactly like present-day Venus, a baked, sterile, dead rock with a superheated atmosphere made entirely of carbon dioxide, with average surface temperatures hovering around a staggering 450 degrees Celsius.
But hey, take a deep breath. Seriously, we do not have to go down with the ship.
According to me, our ultimate survival begins right next door. And the wildest part? It is starting immediately. The secret to our survival actually lies in an incredible piece of chemistry known as the Sabatier reaction. You see, the biggest fear people have about colonizing Mars is getting stranded on a dead world millions of miles from home. But colonists won't need to bring their return fuel all the way from Earth. They will literally cook it up right there from the barren Martian dirt and air. It reads almost like a simple baking recipe. Step 1. You drill into the Martian subsurface to extract frozen water ice, which gives you vital hydrogen. Step 2. You pull the abundant carbon dioxide straight out of the thin Martian atmosphere. Step 3. You combine them in a reactor to synthesize liquid methane and liquid oxygen. And boom! Just like that, you have created highly efficient rocket propellant. We can build totally self-sustaining gas stations on another planet. And I need to emphasize this isn't just distant science fiction slated for the year 3000. Just look at the SpaceX Starship Martian expansion timeline right here. We're talking about near-term, unfolding history. Uncrewed test landings and robotic infrastructure setups are literally scheduled to start around 2026 or 2027. By the end of this decade, the initial crewed missions will begin constructing habitats and firing up those very Sabatier fuel plants we just talked about. By 2033 and beyond, the architecture is designed to scale to mass civilian transit. We'll be utilizing fully reusable, super heavy lift rockets carrying over 100 passengers per single flight. Yes, the logistics are absolutely staggering, requiring massive orbital refueling operations just above Earth's atmosphere, but the engineering? It's already being tested and perfected today. We are turning multiplanetary dreams into an urgent, tangible reality. But how do we actually turn Mars from a freezing, irradiated desert into a lush, second Earth? Well, Mars lost its atmosphere billions of years ago because its magnetic core died, which basically allowed violent solar winds to strip away its air and oceans. For years, people thought we'd have to magically drill to the core and reignite it with, like, nuclear weapons. But in my view, there is a much more elegant solution. We can simply place a massive artificial magnetic umbrella in space. By floating a 1 to 2 Tesla magnetic dipole at what's called Lagrange point 1, which is just a stable gravitational parking spot where the shield can hover perfectly between Mars and the Sun, we can cast a massive protective magnetic shadow over the entire planet. By simply deflecting those harsh solar winds, the Martian atmosphere will naturally begin to outgas and thicken all on its own. It initiates a greenhouse effect that could melt the polar caps and potentially restore a fraction of Mars' ancient oceans, without us ever having to touch the planet's dead core. However, let's be real for a second. Mastering heavy-lift rockets and orbital magnetic shields, that brings us to our third and perhaps most terrifying hurdle. Because rushing out into the cosmos means absolutely nothing if we can't master the microenvironment and actually keep human biology alive in the void. To understand how incredibly difficult this is, we have to look back at a fascinating and honestly pretty scary cautionary tale from the 1990s, the Biosphere 2 project in the Arizona desert. Scientists tried to pack a functioning Earth ecosystem, complete with a mini rainforest, tiny ocean, and a savanna, into a 3-acre closed glass loop. They sealed 8 people inside, expecting a perfectly self-sustaining paradise. Instead, nature rapidly spiraled into absolute, unmitigated chaos. Within just 16 months, the oxygen levels plummeted from a healthy 21% down to a suffocating 14%, leaving the crew literally gasping for air. Why? Because the unsealed concrete used in the facility's construction chemically reacted with the air, absorbing critical CO2. Without that CO2, the plants couldn't perform photosynthesis to replenish the oxygen. 19 of the 25 vertebrate species died off completely. The vital pollinating insects went extinct. Meanwhile, an invasive species of crazy tramp ants completely took over, swarming the entire facility. It proved a huge point. You cannot just shrink Earth's wilderness into a box. Future space habitats will require rigorous artificial cybernetic controls if we want to survive. And keeping the air breathable is just one hurdle. Once we leave the protective bubble of Earth's magnetic field, we are endlessly bombarded by galactic cosmic rays. I want you to imagine this radiation as microscopic bullet tracks, heavy ions that literally rip straight through our DNA, causing massive cellular damage that leads to rapid cancer and severe cognitive decline. We'll need massive lead shields. Actually, scratch that. Traditional metal shielding like thick lead actually makes it worse, shattering the incoming radiation into a deadly spray of secondary particles. So how do we survive? We use water. Advanced hydrogel spacesuits and habitat walls can trap vast amounts of water in a stable matrix to absorb the radiation without leaking. Furthermore, we're looking at active CRISPR gene editing. Scientists have already successfully tested CRISPR aboard the International Space Station. In the future, we will literally hack our own biology, upregulating radiation-resistant genes and boosting our bone density, effectively turning humanity into a species of spacefaring extremophiles. But once we are fully adapted to space, why would we ever restrict ourselves to settling on suboptimal, dead rocks?
According to me, clinging to the surface of suboptimal planets like Mars is just a temporary phase. Mars only has 38% of Earth's gravity, which wreaks absolute havoc on human bones and cardiovascular systems over long periods. To truly thrive, we won't just settle on dead planets, we'll start building our own perfect worlds entirely from scratch. We can engineer free-floating space habitats that scale up magnificently. Instead of suffering under the heavy gravity of giant planets or the weak gravity of small ones, we build massive structures that spin. Centrifugal force simulates a perfect, flawless 1g of Earth gravity right against the inner hull. We start with early concepts like Island 1, a sphere holding tens of thousands of people. Then we scale up to the O'Neill cylinder, which are massive steel and titanium tubes 8 kilometers across, housing millions of people inside a perfectly controlled, weather-perfect ecosystem. But the ultimate game changer arrives with advanced molecular nanotechnology, bringing us to the sheer, mind-bending awe of the McKendree cylinder.
Look at this number. Just take a second and let it sink in. 76 billion. By utilizing materials like carbon nanotubes, which possess unimaginable tensile strength compared to everyday steel, we could construct a single spinning McKendree cylinder with a radius of over 460 kilometers. The internal surface area of just one of these cylinders would be roughly the size of the United States or Australia. It could comfortably safely house 76 billion humans. That entirely dwarfs the maximum carrying capacity of Earth itself, and all of it contained inside a single continent-sized structure floating peacefully in the void of space. By building these, we become the absolute masters of our own domain. But every magnificent story has a final conflict, doesn't it? Because no matter how incredible our artificial worlds are, no matter how perfectly we engineer our Martian cities or our spinning megastructures, we cannot stop the sun's eventual death. Eventually, our entire solar system will become completely uninhabitable, which means we have to leave our stellar neighborhood altogether. And this leaves us with a monumental logistical nightmare. How do we survive a journey across thousands of light years? The nearest star, Proxima Centauri, is over 4 light years away. Just to accelerate even a tiny ship to 10% the speed of light requires more energy than the entire globe currently consumes in a year. Traditional rockets are entirely useless. Even massive generation ships, where thousands of people live, reproduce, and die over millennia in transit, are incredibly risky. You face catastrophic ecological failures over thousands of years, extreme genetic bottlenecks, and the terrifying sociological risk that descendants will forget the purpose of the mission entirely and descend into factional warfare before they ever arrive. So we bypass the problem entirely. Instead of transporting millions of pounds of living, breathing adults who need food, water, and psychological care for 10,000 years, we use embryo space colonization. We send ultra-fast, incredibly lightweight, heavily shielded ships carrying thousands of cryopreserved, early-stage human embryos. Because embryos require microscopic volume and zero life support during the journey, the ships can travel vastly faster. Upon arriving at a new star system, fully autonomous robots build the first settlement. The embryos are then gestated in advanced artificial wombs. The very first generation of human beings on a new world will be birthed, educated, and raised entirely by highly advanced artificial intelligence and robotic caretakers equipped with the digitized archives of all Earth's history, culture, and science. It is a mind-bending, yet incredibly efficient way to seed the cosmos.
Or, if we achieve the status of a Kardashev Type II civilization, meaning we can control the total energy output of our star, we might not leave our solar system at all. We might just take the whole thing with us. Enter the ultimate sci-fi reality, stellar engines. By building megastructures around the sun, we can literally pilot it. The Class D Kaplan thruster is the absolute pinnacle of this idea. It uses massive electromagnetic fields to siphon hydrogen and helium straight off the sun's surface, feeding that matter into an unfathomably huge fusion reactor. It fires one jet into the sun to keep the engine hovering in place, and another jet out into the void, creating enough thrust to physically move the entire sun, like a giant spaceship engine, and drag all the planets with it across the Milky Way galaxy. We literally drive our star system to safety. But let's bring the narrative back to the present for a second. Because before we can launch embryo ships or literally drive our star toward a new neighborhood,
We need a definitive destination. We need a new Earth. And that search is accelerating at a breathtaking pace. We are deploying a relentless succession of increasingly powerful observatories. Right now, the James Webb Space Telescope is analyzing starlight filtering through the atmospheres of distant planets to detect things like water and methane. But soon, things get incredibly precise. In 2027, the Plato Observatory will stare continuously at the sky to pinpoint Earth-sized planets, specifically in habitable zones. By 2031, Ariel will conduct deep chemical surveys of 1,000 alien worlds. And the grand finale arrives in the 2040s with the Habitable Worlds Observatory. This incredible machine will use advanced coronagraphs, internal mechanisms making microscopic adjustments smaller than the width of an atom to physically block out the blinding light of a host star. For the first time in human history, we will be able to directly image an Earth-sized planet and see the thermodynamic disequilibrium in its atmosphere, which is really just a fancy way of saying we will look for gases that shouldn't naturally exist together unless living, breathing things are actively producing them. We will literally be able to look across the void and see the atmospheric breathing of a living alien biosphere.
So, as we stand here today looking up at the night sky, fully aware that the clock is ticking on our beautiful, fragile home, we are left with a profound choice in how we view our destiny. Is the inevitable death of our planet the tragic end of the human story? Or is it simply the forced eviction we desperately need to finally step out of our cradle and conquer the stars? According to me, humanity is just getting started, and I want you to think about that. Make sure you subscribe and hype this video if you want to hear more such exciting story. Thank you so much for exploring the boundaries of our future with us, and we'll see you out there among the stars.